because I sensed all of you like quadratics. So let's do another problem with the quadratic again. Pardon? Yes, that is a spring. Let's do something, call this theta, and let's make this 53 degrees. The spring here, it's ideal. The spring constant, Spring constant is basically, it's a stiffness constant. It tells you how easy is it to actually move, to expand or to compress the spring. So we'll make this 40 newtons per meter. So what that says is it takes 40 newtons in order to either compress it a meter or stretch it a meter. Now, unlike real springs, Slinky being a classic example of that, in an ideal one I can stretch it as far as I need to, or I can compress it as far as I need to. In real life, it will eventually interfere with itself in real life. However, for an ideal spring, it will not interfere with itself. We will need a mass here, so why don't we stick with 4 kilograms. Let's put this on Earth 2 because there are enough other issues besides multiplying times 9.8, Earth 2. So G, 10 meters per second squared. So we're going to start out the problem with no friction. And I know you're disappointed, you wanted friction from the start, but just relax, we'll get there. The question is, how much will the springs compress? So, what? You know how to do it already?
No, my brain hurts. No, we haven't even started.
All right, let's think about the forces that will be acting on the box. Again, no friction to start out the problem. We're going to magically throw friction into it in a moment. I don't know why I do it like that.
The way you acting down. And a normal force acting that way.
And when it hits the spring,
Acting up the ramp.
yeah. All right, so we're going to put this little F sub E. So, actually, not F sub E, F sub S. The reason why I use S and not E, I think E for elastic, but the subscript E I'm reserving for 152, where E is for electric. So S for spring. The mass is going to come cruising down, hit the spring, it's going to compress. So the more you compress it, the harder, the more force it takes. So it takes 40 newtons to compress it 1 meter. It takes 80 newtons to compress it 2 meters, 120 newtons to compress it 3 meters, and so on. These 3 forces here, one of which is non-conservative, the other 2 are conservative. Which of these is non-conservative? No, that actually is conservative force.
Friction.
No friction yet.
So the normal force.
Yes, normal force is non-conservative. Now, the normal force is perpendicular to the ramp, but the movement is parallel to the ramp. How much work is being done by the normal force? Right. Because work can only be done if they're not perpendicular to each other, if displacement and force are not perpendicular. So this will do no work. No work. Therefore, the only forces doing work are conservative forces, therefore, energy is conserved. We do not need to break anything up into components. We just need to start with my initial energy equals my final energy, because energy is conserved. What are the two types of energy involved here? Assuming no bursting in the flames.
Kinetic.
And
Potential.
so I got my initial kinetic plus my initial potential is equal to my final kinetic plus my final potential. And it would help if I actually did the right notation there. Final kinetic plus final potential. There we go. What are the two conservative forces involved here?
Gravitational force.
And
Force of the spring.
yes, so I got my spring force and my weight. I have two conservative forces, so I have two potential energy formulas. So this is my initial kinetic plus the initial gravitational potential plus the initial spring potential, and then the same just with the final, plus UG final plus US final. Let's go ahead and do some formulas here. I'm about to ask that question, which all of you should be able to recite back in unison. So do a quick check with your notes if you need to. Here we go. This is for all the international fans. They want to hear that chorus of angels as I do. Here we go. What's the formula for kinetic energy?
1/2 mv squared.
Oh, it's nice. So I got 1/2 mv initial squared. Over here, I got a 1/2 mv final squared. All right. What is the formula for potential energy?
Which one?
The one associated with the gravitational force when you are near the surface of a planet.
Capital G.
That one. That is a generalized gravity. Either you're heading towards the generalized gravitational potential energy or the generalized gravitational force. We're looking when we're dealing with weight.
Oh. MGH.
That's the one. That one. So plus MGH, the initial, and then over here plus MGH final. All right. So now we have the spring force, which we haven't really talked about. I think I wrote it up on the board, but did not give really any explanation for it. The formula looks a lot like the kinetic energy formula, and that's more coincidence than anything else. But it is, and I will go for a different color just to make it pop. I'm sure this will make it pop. Yeah, beige. That does it. 1/2 K, the spring constant, times delta X squared, initial. And then plus 1/2 K delta X final squared. Delta X is how far it is displaced, whether it's compressed or stretched, how far it's displaced from equilibrium. So the spring's just kind of hanging there, doing its thing. This would be the equilibrium. Delta X is how much it's going to compress from that length or stretch from that length. All right, questions before we go to a new page? So I have 1/2 mv initial squared plus mgh initial plus 1/2 k delta x initial squared equals 1/2 mv final squared plus mgh final plus 1/2 k delta x final squared. And so we'll use the board over here. Let me draw the picture so it's a little bit more permanent. I think I made that a 50, theta is a 53-degree angle. I got my spring right here. K was 40 newtons per meter. I had a 4 kilogram box. And this was earth tube. I am gonna make one small change here, and I apologize for this, but instead of making this 4, let's make this 5. Doesn't change anything we've done yet. And the reason I'm doing that is with 4 there, mg becomes 40, and I'm using 40 for that number right there, and if you're looking at your notes, I don't want you to go, wait, which 40 is this? All right, so we've set up the equation. It's now the first step. Let's figure out what's 0.
Speed, right? There's no equal, there's no way don't have speed.
Sorry, louder.
Speed,
You said D?
speed, velocity.
Oh, speed. Okay. Initial speed is 0.
Speed.
I did not state that explicitly, but you read my mind. Thank you. Let's go ahead and make it explicit. Okay. We're looking for maximum, how much will the spring compress? That's what we're trying to find.
Is our delta x initial 0?
Yep. Because the spring's just hanging out, it's doing its thing.
Is, MGH final 0?
You want it to be?
Yes.
Okay. Because Ethan said so. So what he has done is he has established, so the spring's going to compress some amount, we'll just say it compresses to here. So he is establishing H is equal to 0 at maximum compression. Basically, the 2 places I would recommend making H is equal to 0, actually, it could be 3. You could make the initial height 0, the spring, when it's just a normal relaxation state, you could have made that, the end of that 0 or maximum compression. So those are the 3 choices I would recommend. And we got one more thing that's equal to 0.
Is there gonna be our final speed?
Yes, because at maximum compression, that spring, the mass is stopping at that maximum compression.
That's so swag.
That's 0. My final speed is equal to 0 meters per second because of maximum, we're at maximum, was at max compression. If it were still moving, we're not at the maximum compression, or the box has somehow started to move through the spring itself, which generally is discouraged in classical physics. So we've reduced this whole thing down to just 2 terms. See how easy physics is? You just get set a bunch of stuff to 0. We're now down to mgh initial equals 1/2 k delta x final squared. All right, I promised a quadratic. Well, this is a quadratic, but we need to somehow relate, well, m is given, g is given, k is given, 1/2 is given. We have this 2 unknowns here that are not the same. So we need to somehow relate h initial and the amount it compresses. That would be h initial, technically to the center of mass, but good enough. And that is the amount it compresses. So I probably should give one other number here, this distance here. Why don't we make that 2 meters? So it's gonna slide 2 meters before it hits the spring. What is the relationship between my final compression and my initial height?
It, the initial, I mean, the change, the final compression and the two would be the hypotenuse of a triangle with h being the height.
So what trig function involves the opposite side and the hypotenuse? So sine of theta is equal to my initial height over 2 plus x final. So my initial height is just the hypotenuse, 2 plus x final, times sine of theta. We now have enough to solve. So we end up with mg times 2 sine theta plus x. I'm just going to reduce it down to just x instead of having to keep writing the subscript. X sine theta is equal to 1/2 k x squared. We distribute the mg, so I now have, in a color that hopefully stands out a little bit better than beige or peach or whatever that is, 2mg sine theta plus mgx sine theta is equal to 1/2 kx squared. This is for you quadratic formula fans. So now it's just a matter of solving for that. It is a quadratic because I'm trying to find x, that's my unknown right there. I've got an x right there and my constant term. I can get everything, put it in classic, well, I guess standard form. So I have 1/2 k x squared minus mg sine theta x minus 2mg sine theta equals 0. Plug and chug. And again, if you don't know the quadratic formula, I think it's probably, should be at on the first page where I have all the other formulas. Or if I forget, ask. So x equals mg sine theta plus or minus the square root of mg sine theta squared minus 4 times 1/2 k times negative 2mg sine theta. I am really running out of room there. Over 2 times 1/2 k. I think it might be time to plug numbers in. I chose 53 degrees. Again, that's a 3, 4, 5 triangle. The sine of 53 degrees is about 0.8. So this is 50 times 0.8, so this should be about 40. So this would be 40 squared minus k was, oh wait, no, not 40. Yes, it is 40. K is 40, so half of 40 is 20 times 4 is 80. So that's 80 times 2 is 160 times 50 is 800. Somebody's going to tell me. That's going to be 40. All right, so 4 times 20 is 80. 160. 160 times 5 is 800 times 10 is 8,000 times the sine of, so that was 8,000 times 0.8, so this is. Something's not right there. Oh, that's right, it's a plus, because I got the two negatives, plus 6,400. 1,600, 6,400 is 8,000, square root of 8,000, whatever that is. Assuming I haven't made a calculus error in my head, this whole radical becomes square root of 8,000. We will get two answers. The answers are. Alright, square root of 8,000, square root of 80 is about 9, so that's roughly 90, so 40 plus or minus 90-ish. 40, so 130 over 40, so I'm getting 4.23, or negative 90 is 30, negative 0.76. And I quite easily could have made a Daryl's error. What do people have? So this is 20x squared minus 50 times 0.8, so minus 40x. And then 100 times that, so minus a third. What'd you get?
41.93.
Say it again?
41.93.
41.93, that's definitely different from what I was getting. So you get 40.93,
And the second one has an imaginary number, so that's wrong.
if one is imaginary, the other one's imaginary.
I got 3.236 and negative 1.23.